Welcome to the deep dive. Today, we're launching into the really fascinating world of low Earth orbit, ELO, you know,
Yeah.
mega-constellations.
Yeah, those huge satellite networks are already doing so much GPS, internet reconnaissance.
Exactly. But what's really exciting now is how they're changing. They
Yeah.
could potentially reshape how we see Earth, how we use satellite tech altogether.
Absolutely. And the scale is just incredible. We're moving past just, putting satellites everywhere.
Right.
The new challenge is designing them for specific, really demanding tasks. Think like ultra high-res images whenever you need them, or moving huge amounts of data super fast.
And a whole new level of complexity, isn't it?
Definitely.
It's not just about coverage anymore. It's about being smart, being in the right place for a specific job.
Precisely.
And that leads us perfectly into our deep dive today.
Yeah.
We're looking at a really interesting study.
Yeah.
Came out recently in Space. Science and Technology.
Ah, yes, the one from the collaboration, Harbin Engineering University.
That's the one. And the China Academy of Space Technology, plus Stevens Institute of Technology.
Right. And they've come up with a really novel approach thinking about how to coordinate these orbits differently.
How so?
Instead of just individual satellites doing their own thing, they're looking at grouping them. Smarter, more flexible groups. It opens up some really groundbreaking possibilities for Earth observation.
Okay, so that's our mission for this deep dive then. Let's really get into this new design method. What's the idea behind it?
Yeah, what makes it different?
And what kind of leap forward could it mean for, how we watch our planet? All right, let's unpack it. What is the fundamental idea here?
So the main innovation is this concept they call grouped satellites.
Grouped satellites.
Yeah, they basically organize the constellation into two kinds of satellites, basic ones and accompanying ones.
Okay.
You can sort of picture it like a leader satellite with its own little support team orbiting around it.
Interesting metaphor. So how do these groups, these satellite teams, actually get arranged up there? Can you paint a picture?
Sure. So imagine each basic satellite is like the leader of a group.
Right.
And it has a cluster of these accompanying satellites orbiting it. Then these complete groups are spread out evenly around the Earth.
Evenly spaced. Got it.
And here's a key part. All the basic satellites follow the exact same path over the ground, the same sub-satellite trajectory.
So that gives you consistent, predictable global coverage as a baseline.
Exactly. It's the foundation.
There's a satellite group, the basic one plus its companions. That's the core building block, not just individual satellites anymore.
That's it, precisely. It's the unit that gets replicated. Now, figuring out the best orbits for those basic leader satellites, for that they used a model called a regression orbit.
Regression orbit. Okay, what's the key idea there?
Sounds technical.
It is a bit, but think of it like setting a really precise schedule for the satellite's path.
Okay.
A regression orbit is calculated so the satellite completes, let's say, exactly R orbits in exactly D days.
Okay. Highly predictable. Very. You get repeatable ground tracks. And importantly, the model isn't just for a perfect sphere. It accounts for Earth's, gravitational bumps and wobbles.
The geoid isn't perfectly round yet.
Right. Factoring that in helps keep the basic satellite's orbit stable over the long term, keeps them on that reliable schedule.
That makes a lot of sense. Need that stability for consistent coverage. Okay, so they've planned the basic orbits. How do they figure out how many of these paths they actually need to cover the whole planet?
Good question. That comes down to the imaging swath width of the entire satellite group.
The group's view, not just one satellite.
Correct. Imagine the whole group acting like one big camera. The swath width is how wide a strip of Earth it can see as it passes over.
Okay.
So you compare that group swath width to the Earth's circumference, basically, and that tells you the minimum number of orbital paths you need so no spots are missed.
Got it. So we have global coverage sorted with the basic paths. But you mentioned responsiveness earlier, getting data fast.
Yeah.
How does the grouped approach help there?
That's where the number of basic satellites along each path comes in.
More satellites on the same track.
Exactly. The more basic satellites you put on a single orbital path, the more often a group will pass over any given point.
Which means shorter waiting times if you need an image or data from that spot.
Precisely. It just ups the odds that a group is nearby when you need it. Better timeliness.
Right, more basic satellites equals faster revisit. Okay, now let's zoom in on those accompanying satellites. You said they have elliptical trajectories relative to the basic ones. How does that work?
Yeah, their motion relative to their basic leader satellite is described by something called the Clohessy-Wiltshire equation. It's pretty standard for modeling relative motion in orbit.
Okay.
Essentially, it predicts they'll follow an elliptical path around the basic satellite.
And how do they figure out the specifics of that ellipse?
So, for the first accompanying satellite in a group, they determine its orbital elements, the things that define the ellipse's shape and orientation, by looking at where they want it to be relative to the basic satellite at the start, and then again half an orbit later.
Sort of defining the extremes of its relative path.
Kind of, yeah. It locks in that specific, predictable dance around the central satellite.
Okay, so that first companion's path is set.
Right.
What about the rest of the group? The other accompanying satellites, how many are there? How are they positioned?
Right. So the number of accompanying satellites in a group, they call it NA, depends directly on how wide a total observation range you want, let's call that NA, and how wide a single accompanying satellite can see, SD.
Okay, so it's based on the desired coverage width.
Exactly. The formula is basically NA equals the ceiling of D divided by SD minus 1.
Ceiling meaning round up.
Round up, yeah. To make sure you have enough satellites to fully cover the desired width D, even if it doesn't divide perfectly, you need enough side-by-side views.
Makes sense. And their positions relative to each other.
That's clever, too. They essentially take the calculated trajectory of that first accompanying satellite and create time-shifted copies of it for the others.
So they follow the same relative path, just staggered in time.
You got it. If you know where the first one is at any point, the others will be at those same relative spots, just a bit earlier or later. It ensures they work together as a coordinated team within the group.
That paints a really clear picture, a kind of orbital ballet. Now, designing all this, these complex orbits, it must take some serious computing power, right? The study mentions optimization algorithms.
Oh, absolutely. Getting that initial blueprint with the grouped idea is one thing, but then they use optimization algorithms to really fine-tune it, make it perform even better.
And which one did they use?
They specifically use the non-dominated particle swarm optimization algorithm. It's, quite a mouthful.
Okay, particle swarm optimization. Let's break that down. Sounds almost biological.
It kind of is, in principle.
Yeah.
Think of a flock of birds searching for food. Each bird is like a potential solution, a slightly different way to arrange the constellation's orbits. They fly around and they communicate, right?
Yeah.
They share info about where they've found good spots.
Right, they learn from each other.
Exactly. So over time, the whole flock tends to move towards the most promising areas. In our case, the promising areas are better constellation configurations.
And the non-dominated sort part.
That comes in because usually there isn't just one single best answer.
Oh.
We have multiple goals we're trying to achieve simultaneously,
Yeah.
like keeping the basic satellites evenly spaced and keeping the accompanying satellites tightly grouped. Sometimes improving one might slightly worsen the other.
Trade-offs.
Right. So this method helps find a set of solutions, the Pareto-front, where you can't improve one objective without sacrificing something on another. It gives you the best possible trade-offs.
Okay, so what specifically are these optimization objectives? What makes one configuration better than another for the algorithm?
Good question. There are two main ones they focused on. First, for the basic satellites, Objective F1, the goal is to minimize the difference in their ascending and descending nodes.
The equator crossings, right, to keep them evenly spaced around the globe.
Precisely. Keep that global pattern consistent. The second objective, F2, is for the accompanying satellites. The goal there is to keep their relative positions within their group as stable and consistent as possible over time.
You want the team to stay in formation.
Exactly, for that coordinated observation to work effectively.
So how does this particle swarm actually, find these optimal solutions? What's the process like?
It's iterative. It repeats over and over.
Okay.
It starts with a bunch of random potential solutions, random constellation designs. Then, in each cycle, every particle, every design, adjusts its own parameters, its orbital details.
How does it know how to adjust?
It learns from two things: its own best performance it's achieved so far, and the overall best performance achieved by any particle in the whole swarm up to that point.
So it uses its personal best and the group's best as guides.
Exactly. It's constantly learning and nudging itself towards better configurations based on those two pieces of information.
So it's this cycle of refinement, tweaking the designs based on those two objectives, spacing and formation.
That's the core idea. And this repeats for maybe a set number of generations or until the improvements start to level off.
And the end result is that Pareto-front you mentioned.
Yes, that collection of optimal solutions, each representing a different balance between the objectives.
And then the designers can look at that set and pick the configuration that best suits the mission's specific priorities.
Precisely. It offers a choice of high-performing options. Now, to really check if this whole method works, they ran a big numerical simulation.
Right. Put it to the test. What were the parameters? What kind of scenario did they model?
Okay, so they set the orbital inclination at 66 degrees. Perfectly circular orbits, so eccentricity 0. They set a specific regression rate, Q equals 15, simulated it for 1 full day.
And the observation capabilities.
They defined the imaging width for a whole satellite group as 1,500 kilometers. For a single accompanying satellite, it was 140 kilometers, and they set a maximum working time per orbit of 35 minutes.
Okay, pretty detailed setup. What did they find? What were the key results from the simulation?
Well, one interesting thing they saw during the optimization itself was how quickly the algorithm found good solutions, that Pareto-front approximation. It happened pretty fast in the early generations.
So it converged quickly towards good designs.
Yeah, and then it stabilized, suggesting it had found the best possible trade-offs efficiently. That speed is promising for designing these complex systems.
That is good. And the final constellation they picked from the simulation, what does it look like?
The final configuration they selected ended up having 891 satellites in total.
Wow, almost 900. How are they arranged?
It broke down into 81 basic satellites, spread evenly in their orbits. And then around each of those 81 basic satellites, there were 10 accompanying satellites, also evenly positioned within their little groups.
10 companions for each leader. So that's 810 accompanying satellites plus the 81 basic ones.
Correct.
And what kind of observation power does nearly 900 satellites working together like that actually provide?
Well, the simulation showed that those 810 accompanying satellites working together in their groups could observe pretty much any spot on Earth outside the polar regions within just 35 minutes.
35 minutes. That's incredibly responsive.
It really is. It highlights the potential for very high revisit rates and comprehensive coverage with this grouped approach.
Okay, so let's just quickly recap. The big innovation here is this grouped satellite idea, right?
Yeah, the basic satellites for the global grid, the accompanying ones for flexible, rapid response.
All orchestrated using this swarm optimization to find the best configurations. It's a really different way to think about building these massive constellations.
Exactly. It's a big step towards making LEO constellations not just numerous, but intelligent, adaptable, suited for really specialized Earth observation tasks.
It really is groundbreaking stuff. It makes you think, doesn't it?
Yeah.
How this kind of sophisticated design might change things. Not just giving us better pictures or faster data, but fundamentally changing how we interact with the planet. Think about, say, environmental monitoring, tracking climate change in near real time.
Or disaster response. Getting eyes on scene almost immediately.
Yeah.
Managing resources like agriculture more effectively.
Yeah, the possibilities seem huge. What new things become possible when you have this level of coordinated observation from space? It's definitely something powerful to think about. Thanks for taking this deep dive with us today.